Okay, what we want to look at now is moving into solving differential equations. And what that means is we looking at, in this particular case, finding the solution for y. Okay, so we're given a differential equation and we want to find, okay, what's my value of y, or what's my expression for y that gives me that particular differential equation. So in other words, if we've got dy dx equals x over 1 plus x squared, then in order to find y, I'm going to have to anti-differentiate. So I need to integrate both sides with respect to x. Okay, so integrate both sides with respect to x. So on the left hand side I have the integral of dy dx with respect to x, and on the right hand side I have the integral of x over 1 plus x squared dx. The left hand side becomes y, okay? Because if we just anti-differentiate dy dx, we get y. Okay, so the right hand side then we need to work our way through. And this type of problem, okay, if we look at the numerator, the denominator, we might think, this is arctan, but that's only the case if we have a constant term in the numerator. We have instead x, so hopefully we can recognise that we can use a substitution method in this case. So we're going to let u equal x squared, or even 1 plus x squared. Which means that du will equal 2x dx. Alright, so we need, then we've got here x dx, but we want 2x dx over 1 plus x squared, but because we've introduced a 2 here, we need to counterbalance that, so multiply by 1/2. Progressing further, we can see now that 2x dx is the same as du, and 1 plus x squared we know is u, so we have 1/2 times the integral of 1 over u du. And going further, we can see that that's 1/2 times the natural log of u plus c. And then we can substitute back. We know that u is 1 plus x squared, so it's 1/2 log of 1 plus x squared plus c. And that's our solution. Okay. All right, let's look at another example. Example 5 now. All right, we're going to look at now the second example in this particular set of differential equations. And this problem we've got is the rate of change of a shaded area covered by a shrub is modelled by the differential equation given here, where A in square metres is the area covered by the shrub T months after it is planted. If the shrub covers an area of 0.3 square metres when planted, what area does it cover after 9 months? Let's have a look at what information we've got. We've got a differential equation, dA dt. What is that telling us? Okay, this expression is describing the rate of change, okay, of the area with respect to time. Okay, that's what it says here, the rate of change of a shaded area covered by the shrub. Okay, the question's asking us to find what area does it cover. So we need to have an expression or an equation for area and then find the actual area. So, given the rate of change of the area with respect to time, we need to find the area. We're going to have to anti-differentiate. We need to solve this differential equation for A. Okay, so let's start at the beginning. A is going to equal the integral of dA dt with respect to time. Okay, and that's going to equal the integral of 0.02 t plus 0.5 sine pi t over 6. All that with respect to time. Now, we can go ahead and integrate the right-hand side. Okay, we've got our first function here, so that becomes 0.02 t squared over 2. Now the integral of sine is negative cos, so it's minus 0.5 times 1 over pi on 6, which is 6 over pi, cos pi t over 6 plus c. Simplify that a little. This becomes 0.01 t squared minus 0.5 times 6 is 3, so that's 3 over pi cos pi t over 6 plus c. So what we have here is an expression for the area, the shaded area covered by the shrub. Okay, so but we have this constant term c. We need to basically find out what that is, and that's where we go back and think, what information have we been given? We've got the shrub covering an area of 0.3 square metres when planted. So in other words, when t equals 0, A equals 0.3 square metres. So 0.3 equals 0.01 times 0 squared minus 3 over pi cos pi over 6 times 0 plus c. So 0.3 equals, now that's 0, and we're left with minus 3 over pi cos of 0 plus c. So 0.3 equals, cos of 0 is 1, so it's minus 3 over pi plus c, so that c equals 0.3 plus 3 over pi. And that is approximately 1.255 to 3 decimal places. Okay, so then we can say that the area is equal to 0.01 t squared minus 3 over pi cos pi t over 6 plus 0.3 plus 3 over pi. Or given that we're finding the area at the end, we could use our approximate value, so I'll get rid of that and I'll put in 1.255. Okay. Now, if t equals 9 months, a equals 0.01 times 9 squared minus 3 over pi cos pi over 6 times 9 plus 1.255. And we can put all that in our calculator and get a nice answer of 2.065. And so we can therefore say after 9 months the shrub covers an area of 2.065 square metres, approximately. Okay, so those are typical sort of problems where we have our the form of our differential equation as being equal to some function of x. Okay, just a function of x. Okay, here in our first example we've had on our right hand side we've got a function of x because all we have on the right hand side is x in terms of the variable. Okay, and same with the next one. Okay, it obviously wasn't x this time, it was t, but it was a function of a single variable. Okay, in this case t. Okay, so these types of problems then we can work through exercise 7c, and that's page 317 of your text. Okay, and we'll leave it there for this video.